mode.
So good morning to all of you. I am Dr. Rama Krishna from Keele University, and this is a trial lecture on heat transfer. So this session mainly deals with identifying the differences between thermodynamics and heat transfer, and what are the different modes of heat transfer, and what is Fourier law of conduction, and what is thermal conductivity. At the end of the session, the student will be able to distinguish between the courses thermodynamics and heat transfer. He will be able to understand the basic mechanisms of heat transfer, and he will be able to identify the heat transfer mechanism that occur in nature, and he will be able to apply Fourier law of conduction to different systems to calculate the heat transfer by means of conduction, and he will be able to compare the thermal conductivity of different materials and understand the significance of air in different heat transfer process. So coming to the first item, thermodynamics versus heat transfer. Most of the students might have studied in their first year course thermodynamics. Thermodynamics also deals with transfer of energy, basically heat and work. We study heat transfer in thermodynamics, and again, why should we study the heat transfer as a separate course? In thermodynamics, the study deals with the amount of heat transfer as a system undergoes one process from one equilibrium state to another equilibrium state. For example, you consider a hot steel ball, maybe around 100 degrees centigrade, which is dropped in a beaker of water. The 100 degrees centigrade steel ball will reach a temperature of 20 degrees centigrade and attain equilibrium with that of water. So how much heat has been lost by the ball to attain the equilibrium? You can use the equation Q equal to mCp delta T to calculate the heat lost by the steel ball to attain the equilibrium condition. But how much time it has taken to reach the equilibrium? We can't determine using thermodynamic equations. Similarly, maybe after a few seconds, before it reaches equilibrium, what is the temperature of the ball? We cannot identify using thermodynamic expressions. So when you want to relate the rate of heat transfer and you want to identify the time involved in attaining equilibrium, you have to separately study the subject which is known as heat transfer. So heat transfer deals with the determination of rates of such energy transfer. That is the reason why in thermodynamics heat is measured in joules or kilojoules, whereas in heat transfer it is expressed in terms of joules per second or kilojoules per second. That means in watts. What are the different modes of heat transfer? The rate of heat transfer takes place by three modes. One is conduction, the other one is convection, and the third mode is radiation. All these modes of heat transfer occurs only because of temperature difference. We know that heat always flows from high temperature to low temperature. Whenever there is a temperature difference, the flow of heat is identified by these three mechanisms. How exactly these three mechanisms takes place? Let us take a point A where material is placed. Maybe a group of stones are located at A. I stones from A to B, which is 50 meters away from the point A. I will think of three different ways. First case, Let us employ 100 workers to move these stones from A to B. All these 100 workers are made to stand one after the other. The approximate distance between each one will, so they are very close. So the first person picks up the stone and hands it over to the next, and then to the next, etc. After some time, the entire stones will be transferred from A to B. So the persons are not moving from their position, but the stones are transferred from A to B. A is considered as high potential zone, and where B there is no material, it is a low potential zone. All these stones are transferred from high potential zone to low potential zone without any motion of the workers. That kind of heat transfer which occurs from high temperature zone to low temperature zone without any relative motion of molecules is known as conduction. Normally occurs in solids. Of course, you can have conduction in gases and liquids. We will see it later. The second mode, imagine that particular day only 10 workers are available. So when you have only 10 workers, when you ask them to stand from A to B, the relative distance becomes 5 meters. So it is not possible to transfer the bricks or stones without motion. So in the case 2, these 10 workers individually, each one will pick up the stone at A, walks all along the way from A to B, leave the stone here, he will come back and then pick up the stones from A. Like that, molecules pick up the heat from high temperature zone, go to the low temperature zone, leave it there, and again he will come back and pick up the heat. That kind of transfer of energy which occurs due to motion of molecules picking up heat from high temperature zone and leaving it at low temperature zone is known as convection. The second mode of heat transfer, which happens in case of liquids and gases where there is motion of molecules is predominant. You imagine in the case of convection, or when only 10 workers are there, if there is no supervisor, workers move on their own and it may take a little more time when compared to with the supervisor. If a supervisor is there, he will force the workers to move fast, thereby the transfer of energy or transfer of material takes place quickly. That kind of motion of molecules driven by some external force is known as convective heat transfer under forced conditions, and that is called forced convection. So the example of 10 workers moving material from A to B with a supervisor falls under the category of forced convection. Without supervisor, if they move on their own, transferring the material, it is analogous to natural convection or free convection. In the third case, imagine there is no road between A and B. Imagine there is a big valley between A and B. Then to transfer these stones from A to B, the person will pick up the stone and throw it in air so that it will fall at B. That mode of heat transfer, which requires no medium to transfer energy from one point to another point, with the help of electromagnetic waves carrying the energy, is known as radiation mode. In fact, medium is an obstruction for radiation. While throwing stones from A to B, imagine some birds are flying, so we cannot throw properly the stones from A to B. So medium is an obstruction for radiation. In vacuum, radiation is dominant. We receive the energy from sun by means of radiation through the vacuum, the space. Now let us go to the conduction. The first mode of heat transfer. We'll see some details in it. If you look at this figure, if you keep a solid steel rod in the fire, the end of the rod gets heated up and that heat is propagated through the rod and reaches the hand. This mode of heat transfer, which occurs without any motion of the molecules within the body, is known as conduction heat transfer. If you observe in the second case, convection, the hot air molecules move and they will come in contact with the hands and we feel the heat. The heat is transferred by the air molecules carrying heat energy from the flame to the hands of the people. So that mode is called convective heat transfer. If you keep your hands a little far away, the electromagnetic waves emitted by these high temperature flames will reach, and we call it as radiation heat transfer. So in the conduction, where we have seen that motion, the heat transfer occurs without any relative motion, let us assume a wall is separating outside and inside room environment. Outside temperature is very high and inside the room the temperature is very low. So heat transfer takes place from outside to the room through the wall without any motion of the molecules present in the wall, and that mode of heat transfer is called conduction. If the area of the wall is large, more amount of heat leaks into the room from outside. So the rate of heat transfer is directly proportional to the area of the wall. If the temperature difference outside and inside the room is more amount of heat will enter into the room. So Q is also directly proportional to delta T, temperature difference. If the thickness of the wall is large, it restricts the heat transfer. So therefore, Q is inversely proportional to delta X, thickness of the wall. Hence we can write Q is directly proportional to area, directly proportional to temperature difference, and inversely proportional to thickness. I can reduce this Q by A is directly proportional to minus dt by dx. In limiting case where delta x tends to 0, delta t by delta x becomes dt by dx. This Q by A, rate of heat transfer per unit area, is known as heat flux and is denoted by small q. The heat flux is directly proportional to dt by dx. Minus sign is introduced because if you look at this figure, in the positive x direction, the temperature drops because heat always flows from higher temperature to lower temperature. To make that transfer of heat in positive x direction as positive, the minus sign is indicated. So this equation says the rate of heat flux is directly proportional to negative temperature gradient, or you can say the moment you remove the proportionality, you have to introduce a constant K. Q is equal to minus K A dt by dx. This is the equation to determine the conduction rate of heat transfer, where K is equal to Q dx by dTA and is known as thermal conductivity. The unit of thermal conductivity is watts per meter Kelvin. Q is in watts, dx is in meters, dt temperature difference in Kelvin or degree centigrade, area is meter square. So it comes down to watt per meter Kelvin. This thermal conductivity K is a material property. Suppose thermal conductivity of copper 400 watts per meter Kelvin. That means you take one unit area of copper plate having unit thickness. Per degree temperature difference across its faces, it can conduct 400 watts of heat transfer. Thermal conductivity of steel is around 60 to 80 watts per meter Kelvin. So steel conducts less heat when compared to copper. While using the equation Q is equal to minus Ka dt by dx, the area A in this is the area normal to the direction of heat transfer. A is the area normal to the direction of heat transfer. For example, if you consider a slab of dimensions LBH, if you want to determine the rate of heat transfer across these two faces, in the equation Q equal to minus Ka dt by dx, in the place of A you have to write the area normal to this heat transfer H into B. If you want to consider the heat transfer across these two faces, the area you have to consider is L into B. So always the area is the area normal to the direction of heat transfer. Suppose a cylindrical surface is perfectly insulated and heat is flowing along the axis of the cylinder. In this case, the area you have to consider is pi r square. Q is equal to K, area is pi r square, the cross-section area, normal to the direction of heat transfer. So conduction is nothing but the transfer of energy from more energetic particles to the adjacent less energetic particles as a result of interaction between the particles. In solids, basically, the conduction heat transfer occurs due to combination of vibration in lattice structures and in energy transport by free electrons. The lattice component of thermal conductivity strongly depends on the way how the molecules are arranged, and the transport by free electrons is in the outermost shell of the orbit. How many free electrons are there? They decide the rate of heat transfer by means of conduction in solids. In liquids and gases, it occurs because of the collision and diffusion of molecules during random motion. What is this thermal conductivity? We have seen that it is a material ability to conduct heat. In the equation Q equal to minus Ka dt by dx, the K is the thermal conductivity of the material through which you want to determine the rate of heat transfer, or the gas or the liquid thermal conductivity. In case of solids, the conduction takes place due to two effects. One is the motion of free electrons, and other one is due to lattice vibrations. The motion of free electrons is highly dominant when compared to the lattice vibrations in conducting heat through solids. For example, you take a material like copper or aluminum. They conduct very large amount of heat, and hence not only they are good heat conductors, they are also good electrical conductors. Because of these free electrons, they become good electrical conductors also. Insulators, if the thermal conductivity is very poor, we call them as insulators or bad conductors. They oppose conductivity and are quite opposite to the conductors. Pure crystals and pure metals have highest thermal conductivity, while the gases and insulating materials have the lowest. In case of crystalline solids such as diamond and silicon, they are semiconductors. They are very good heat conductors, but they are very poor electrical conductors. The another important thing which you have to identify here is when you heat a metal, its thermal conductivity reduces, because the predominant factor in metals for conduction is the motion of free electrons. Whereas in non-metals, you don't have free electrons. The conduction heat transfer occurs basically due to lattice vibrations. So when you heat a metal, the number of free electrons remains same, but at the same time the lattice vibrations increases. With increase in lattice vibration, slightly the conductivity may increase, but the increased lattice vibration impede the motion of free electrons. It arrests the motion of free electrons, thereby drastically the thermal conductivity drops. So when you heat a metal, free electrons remain same, lattice vibrations slightly increases. That increase in lattice vibration arrests the motion of free electrons, hence the overall effect is a decrease in thermal conductivity. Copper, whose is 400 watts per meter Kelvin, exhibits a very high thermal conductivity at 20 Kelvin. It becomes a superconductor and is having a value around 20,000 watts per meter Kelvin. Diamond, which is a highly ordered crystalline solid, has highest thermal conductivity around 2,300 watts per meter Kelvin at room temperature. Unlike metals, diamond and silicon, they are called semiconductors. They have good heat conductivity, but they are rated as poor electrical conductors. That is the reason why, despite of its high cost, diamond heat sinks are used for cooling sensitive electronic components. Another interesting fact here is alloys exhibit low thermal conductivity than parent materials. For example, copper is having a thermal conductivity of 400 watts per meter Kelvin. Aluminum is having a thermal conductivity of 230 watts per meter Kelvin. But an alloy of copper and aluminum, which is known as bronze, having 90% copper and 10% aluminum, exhibits only 50 watts per meter Kelvin thermal conductivity. The phenomena of conduction in gases and liquids is slightly different when compared to solids. In liquids, molecules are closely spaced and hence they exert a stronger intermolecular force field. Thermal conductivity in case of liquids decreases with increase in temperature. Same phenomena like in solids. But anyhow, the exceptional case is water. For water, with increase in temperature, thermal conductivity slightly increases. The thermal conductivity of liquids decrease with increase in their molar mass. Liquid metals like mercury, sodium, lead, etc. have high thermal conductivity when compared to normal fluids, and hence they are used in nuclear power plants for cooling purpose. In case of gases, the division of the molecules and the diffusion of the molecules results in conduction heat transfer. So with increase in temperature, molecules move more faster, resulting in more collisions, and hence for a gas, thermal conductivity increases with increase in temperature, but decreases with increase in mass. So we can say thermal conductivity of gas is directly proportional to square root of absolute temperature and inversely proportional to square root of molar mass. For example, thermal conductivity of helium is much more greater than thermal conductivity of air or argon. Air is a poor conductor of heat and acts as an insulator. Let us have a look at different thermal conductivity values of solids, liquids and gases. As we have seen, diamond exhibits the highest thermal conductivity, 2300, followed by silver around 429 watt per meter Kelvin, copper 400, aluminum 230, iron 80. Non-metals like glass, they exhibit again 0.78, very poor thermal conductivity. See, the density of glass is more than the density of iron. Still, because of less number of free electrons, the glass exhibits poor thermal conductivity. Wood, around 0.17 watts per meter Kelvin only. Polyurethane foam is 0.03 watts per meter Kelvin only. If you take liquids, water has got a thermal conductivity of 0.6 watts per meter Kelvin, and oils exhibit much less than that, around 0.14 watts per meter Kelvin. In gases, air has got the least thermal conductivity, 0.026 watt per meter Kelvin. Of course, nitrogen is the one which is having least thermal conductivity. So therefore, if you observe, air, because of its poor thermal conductivity, it behaves almost like an insulator. So when compared to the polyurethane foam having thermal conductivity 0.03, the thermal conductivity of air is also in the same order. So instead of using a solid material like puff or wood, it is better if you use air for the purpose of insulation. Conductivity can have in solids, liquids and gases. Conduction is highest in solids, relatively low in liquids and least in gases. Therefore, gases can be used as insulators. For example, air is the best insulator. In false roofing, for example, to prevent heat in summer or heat loss from the room to outside in winter, false roofing is the best proposal. By making a false roofing, the air is trapped between the main roof and false roof. When it is in stagnant condition, it prevents the rate of heat transfer by means of conduction, and thereby the room energy is maintained. Instead of covering with single blanket of large thickness in winter to protect yourself from cold, if you cover yourself with 2 layers of thin blankets, it offers more resistance because between the 2 layers, the trapped air acts as an insulator and it arrests the rate of heat transfer. In a thermal power station also, before we supply water to the power plant, we treat it. We deaerate the water and we remove the air completely. Otherwise, the presence of air in the water makes it less thermal conducting and it arrests the heat transfer from hot gases into the water in boiler, and it restricts the condensation also in the condenser. To prevent formation of water droplets or dew formation inside the window surface, 2 layers of windows with glass are used with air in between them, so thereby rate of heat transfer is minimized. Many cold storage walls are constructed in 2 layers with an air gap so that the rate of heat transfer is minimized. So air, being a poor conductor, it acts as an insulator and hence reduces the thermal conductivity. So today in this session we have seen what is the difference between the thermodynamic course and heat transfer course. In thermodynamics we deal heat transfer only by means of total energy transfer, whereas in heat transfer we deal heat energy in terms of rate of heat transfer. Time parameter is introduced. The three basic mechanisms of heat transfer like conduction, convection and radiation we have seen, and the Fourier law of conduction, the heat flux is directly proportional to negative temperature gradient, which results in an equation Q equal to minus Ka dt by dx is covered, and different thermal conductivities of different materials are also seen, and we have identified that air, because of its poor heat transfer, can be used as an insulator in all engineering purposes. Thank you very much.